ever get this close to finishing like a movie online and then suddenly, bam, the streaming service crashes?
Ugh, the worst.
Or how about when you're trying to find a new restaurant and your navigation app just completely loses it?
Yeah, we've all been there.
It's infuriating. But, you know, it really makes you appreciate all the work that goes on behind the scenes to try and prevent those tech meltdowns from happening in the first place.
Totally. It's like building a bridge, right? You don't just build it to hold the weight of the cars. You build it so that if a few key parts fail, the whole thing doesn't come crashing down.
Okay, I like that analogy. So today we're doing a deep dive into the world of fault-tolerant systems and how engineers design that extra layer of, well, fault tolerance.
Exactly.
And we're getting a little geeky with this one. We're looking at a research paper called Fault Tolerance of Metric Basis Can Be Expensive.
Catchy title.
Right. But don't worry, we'll unpack all of that.
Absolutely.
Make sure it all makes sense. So at its core, this paper basically explores how much it actually costs to build in those redundancies, those backups, into a system.
And what they found is that it can get really expensive surprisingly fast.
Exponentially more expensive, right?
Exactly. Like sometimes you add just a little bit of fault tolerance and suddenly you need like way more resources than you would have thought.
It's not just like a linear increase in cost. It's like
it explodes.
Yes, it explodes. Yeah. So to understand why, we need to start with this idea of a metric basis in a network.
Okay, so imagine a grid of sensors, kind of like a giant game of Battleship.
Okay.
And each of those sensors can tell you how far away something is.
Okay, so each sensor is like shouting out a distance. And based on all those distances, you can figure out where something is on that grid.
Yes. And that minimum number of sensors you need to pinpoint the location of anything on that grid, that's your metric basis.
Gotcha.
But here's the problem. If even one of those crucial sensors goes offline, well, the whole system could fail.
And that's where fault tolerance comes in, right?
Yes.
You need some backup sensors just in case.
Exactly. Exactly. Yeah. And so this paper is exploring how many extra sensors would you need to add to handle those failures. And to illustrate this, they use these things called M-graphs.
M-graphs?
Yeah. And what they found is that as you try to make the network more and more fault tolerant, the number of sensors you need, it can skyrocket.
Well, like way more than you would intuitively think.
Way more. It's like, think about adding an extra lane to a highway. It might cost you some money. It might be a little bit of a headache, but it's manageable.
Right.
But with these M-graphs, it's like trying to build a whole new highway system just to handle like a few extra cars.
Wow. Okay, so even though the goal is to make the system simpler in the event of a failure, the actual work of building in that fault tolerance makes the whole thing much more complex behind the scenes.
You got it.
Wow.
And to give you a concrete example, they actually walk through a scenario in the paper where they're trying to make a network fault tolerant to just 3 failures.
Okay.
And what's crazy is that the visual representation of this, the diagram itself, is actually really simple.
Wait, really?
Yeah.
So it looks simple, but the actual math behind it is where things get complicated.
Exactly. And that's like the big aha moment. Even seemingly simple networks, when you start designing for fault tolerance, it can lead to some really big computational challenges.
And this isn't just theoretical. This has real-world implications, right?
Oh, absolutely.
Yeah.
We're talking about the reliability of systems that we depend on every single day. Like, think about something like air traffic control.
Right.
Where even a tiny error could be disastrous.
Okay, yeah. Those cost implications are really starting to hit home now.
Yeah.
So how do engineers ensure that level of reliability, especially for something as critical as air traffic control?
So we're talking about these systems that are super high stakes, right?
Absolutely.
Even a tiny glitch could be a really big deal. So how do engineers make sure those systems are as reliable as possible? So that's where things get even more interesting. So up until now, we've really been talking about like tolerating a single sensor failing, right?
Right.
But what happens if multiple things go wrong at the same time?
Oh.
And that's where this idea of K-metric dimension comes in.
K-metric dimension. Okay. So it's like fault tolerance.
On steroids.
On steroids, yes. Okay. So instead of just having one backup sensor, you're prepared for like 2 or 3.
Or more.
Or even more failing at the same time.
Exactly. Yeah, so the K basically represents how many potential failures the system needs to be able to handle.
Okay.
So a 2-metric dimension means it can lose any 2 sensors and it'll still function. A 3-metric dimension, it can handle 3 sensors going down and so on. And so the researchers wanted to know, okay, Does the cost of this kind of higher level fault tolerance, does that also grow exponentially? Like with
Okay.
those empty graphs we were talking
Oh,
about.
right. So, drum roll, please.
Hmm.
Did they find what they were looking for?
Well, let's just say the results weren't super encouraging.
Oh.
Yeah, so they found that, unfortunately, as you try to make a network tolerant to more and more simultaneous failures, the number of extra sensors you need, again, it just skyrockets. It gets really big, really fast.
So are we talking about needing like a ridiculous number of sensors just to be prepared for like the 1 in a million chance that everything goes wrong at once?
Yeah, I mean, it's a valid question, right? And that's kind of the dilemma that the paper highlights.
Right.
At what point is it just overkill?
Yeah.
And to kind of illustrate this, they actually came up with these even more complex graphs, which they call MTK graphs.
Oh, no, not the MTAK graphs.
Yeah, so imagine those MT graphs we talked about, but now with like an added layer of complexity to account for, multiple failures.
Okay, so I'm definitely not going to try to picture an MTK graph in my head right now. I think that would actually break my brain.
Yeah, don't even try it.
But, okay, I think I get the gist. It's like you're trying to imagine every possible thing that could go wrong at the same time and then build a system that can handle all of those things.
Exactly. You're trying to prepare for every single possibility.
Every single, right.
Which, as you can imagine, is very, very difficult. And so that's where that cost-benefit analysis comes in, right?
Yeah.
At some point, you have to weigh the risk of those multiple failures happening against the cost of building all that redundancy.
So this research is kind of like a reality check for engineers, right?
Yeah.
You want that true rock-solid reliability, especially for these really critical systems.
Wow.
Be prepared to pay a price for it.
Exactly.
Wow.
But here's the interesting thing.
Okay.
While the researchers show how quickly things can spiral out of control cost-wise, they also acknowledge that there might be a better way.
Oh, a better way. Like a shortcut we didn't know about. Tell me more. A better way. So there's hope. We're not doomed to choose between like bankruptcy and constant system crashes. Tell me more about this better way.
Well, it's not like the paper lays out a step-by-step solution or anything, but it kind of throws down a challenge, to engineers, to researchers.
Yeah.
It's saying, hey, the way we're approaching fault tolerance now, yeah, it works, but it might not be the most efficient way.
Okay.
Like, there could be totally new ways to design these systems, right, where we can get the same or even better reliability, but without all those crazy costs.
It's like finding out there's a shortcut on your commute that you never knew about.
Exactly.
Okay, but how does all of this impact us out here in the real world? I mean, I'll admit, this all feels very behind the scenes, even for a tech topic.
Yeah, most of us, we don't really think about the nitty-gritty of like fault tolerance math on a daily basis, right?
Right.
But think about like how much you rely on your phone, your car, your home Wi-Fi.
Okay, probably more than I should.
Exactly. All of those things are relying on these super complex systems that have to be fault tolerant to some degree.
Right.
But let's take an example that's maybe a little more dramatic, like self-driving cars.
Okay, yeah. I can see where fault tolerance would be non-negotiable in that situation.
Absolutely. So those cars are using sensor networks for everything, right?
Right.
To see what's around them, to avoid obstacles, to like make split-second decisions.
Yeah.
And the level of fault tolerance that's required there is insane because even a tiny error
Could be really bad.
could be catastrophic. Yeah,
Right, yeah. The stakes are so much higher when it's literally about human lives.
exactly. And as those kind of technologies become more and more common,
Right.
understanding these kinds of cost and complexity issues, it becomes crucial, It's
Yeah.
not just for the technology itself, but for like public safety.
Right, absolutely.
And this applies to so many things,
Yeah.
Medical devices, industrial control systems, even like financial networks.
Right.
The more complicated our world gets, the more we rely on all this stuff working perfectly.
Yeah.
The more we need to be thinking about these trade-offs, right?
Yeah.
Between cost, complexity, and safety.
It's like this research is sort of giving us a glimpse into the future of technology and kind of urging us to have these conversations now about how much risk we're okay with and how much we're willing to invest to prevent those what-if scenarios.
And I think the coolest thing about this paper is it doesn't just present a problem.
Yeah.
It starts a conversation.
Yes.
It makes us actually think about all the technology that we use every single day.
So the next time your internet crashes or your favorite app freezes, remember this research, right? Yes. There's this whole hidden world of complex math and engineering that's going on behind the scenes to try and stop those failures from happening.
Absolutely. It's amazing how much goes into it when you think about it.
I know. And sometimes, achieving that like rock solid reliability,
Yeah.
it comes at a price.
It does. For all you listeners out there, the next time you're using your phone, crossing a busy street, even just trusting your GPS to get you home safe,
Right.
think about all the systems that have to work perfectly for you to do those everyday things.
Right.
How much redundancy do you think is built into those systems?
Right.
And how much would it cost to make them, truly infallible?
Such a great question. And on that note, we'll leave you to ponder those deep thoughts. Thanks for joining us on this deep dive into the world of fault-tolerant systems. Until next time.
Ever wonder just how reliable, like really reliable, that network of sensors you're relying on actually is?
It's something most people don't think about until something goes wrong, that is.
Right. Things are quietly everywhere doing their thing.
Yeah.
In everything from, smartphones to those self-driving cars everyone's talking about.
And when we talk about reliability in those contexts, well, we're talking about situations where accuracy is crucial, mission critical even.
Absolutely. So today, we're doing a deep dive into some fascinating research to uncover just how many sensors you actually need to be confident, to have some peace of mind that the network's going to stay accurate even when things go sideways.
And inevitably, things will go sideways.
Exactly. The paper we're looking at is titled, Fault Tolerance of Metric Basis Can Be Expensive.
Catchy, right?
I'll say. And trust me, that title isn't hyperbole. But before we get into the nitty-gritty, we need to lay some groundwork. This paper dives headfirst into a concept called metric dimension, which I'll admit sounds a bit intimidating at first glance.
Yeah, it's one of those technical terms that can make your eyes glaze over.
Right. But bear with us, because it's actually pretty intuitive. Think about it like this. Imagine you need to pinpoint a location on a map, any location. You need coordinates to do that, right?
Latitude and longitude, they tell you exactly where you are.
Exactly. Metric dimension is kind of like that, but for networks. It's essentially the bare minimum, the absolute minimum number of reference points you need to be able to accurately locate anything within that network.
And in the world of sensors, each one of those reference points is like, well, a data gathering sensor.
Okay, so more sensors, more information. Seems like a good thing, right? More is always better.
In a perfect world, sure, but the real world, as we know, rarely cooperates with our ideal scenarios.
Because sensors, like any piece of technology, are prone to failure. They break down, they get glitchy, they have an off day.
And that's where things get really interesting. That's where this whole fault tolerance idea comes into play.
And that's where the expensive part of the paper's title comes in.
Precisely, because when we're talking about making sensor networks more resilient, more fault tolerant, we're essentially talking about redundancy.
Having backup plans for our backup plans.
Exactly. It's about figuring out mathematically the absolute minimum number of sensors you need to guarantee accurate data, even if some of those sensors decide to take an unexpected vacation.
So we need to figure out how much redundancy is actually enough, and how much is that going to cost us?
Exactly. And that's where the researchers uncovered some pretty surprising results. For some common network layouts, it turns out achieving fault tolerance isn't really that bad. Think about like networks that are structured like trees.
Branching out.
Right, branching out like a family tree. Or complete multipartite graphs, which, imagine groups of friends where everyone in one group knows everyone in the other groups. It's kind of like that in network terms.
Okay, so for these types of networks, doubling up on sensors isn't a huge deal.
Yeah, in those cases, you might only need to double the basic sensor count, just to get that extra layer of reliability, but that's the whole.
There's always a but, right?
Right. The researchers' key finding, their big takeaway, is that in the absolute worst case scenario.
And by worst case, you mean?
I mean, the absolute most difficult, most extreme situations, they found that in those cases, you could need an exponential increase in the number of sensors.
Exponential. So hold on. We're not just talking about adding a few extra sensors here.
No, exponential growth means things escalate quickly, like really quickly. If you need, say, 2 sensors for basic accuracy, you might need 4 to be fault tolerant, then 8, then 16. It can get out of hand fast.
Wow. Okay, so instead of a dozen sensors monitoring a factory floor, we might need Hundreds, even thousands.
It's possible. And that's why this research is so important. It highlights the fact that those simple assumptions we might make about reliability, they can be very, very wrong, especially when you're dealing with complex systems.
Right. So how do they figure this out? How do you even begin to study these worst case scenarios? Did they build some kind of sensor chamber of horrors?
Well, not exactly a chamber of horrors. They focused on mathematical models of networks, specifically graphs. To push the limits, they actually created special types of graphs called MT and MTK.
Catchy names.
Right. But these graphs, they act like stress tests. They show us just how many sensors you would need in the most extreme situations. Like if you were designing a building to withstand the worst possible earthquake.
Even if it were incredibly unlikely.
Exactly. By creating these incredibly challenging scenarios with the MT and MT graphs, they were able to mathematically prove that this exponential increase in sensors is sometimes necessary.
So they've shown that things can get really complicated really fast. But this all hinges on those worst-case scenarios. What about the average case? Where do most real-world networks fall on this spectrum of, sensor needs? That's the billion-dollar question, isn't it? How do we take this theoretical worst-case scenario stuff and actually apply it in the real world?
It comes down to risk assessment, really, and recognizing that our intuition about these things can be flawed.
Because it's easy to fall into that trap of thinking, oh, a few extra sensors should be fine.
Right. But this research tells us that in some cases, a few extra might not even scratch the surface. It's about understanding the potential for things to get really complex really quickly.
So due diligence is key. But where do we even start?
Start by asking the tough questions. Where does my network fall on that spectrum of reliability? Am I dealing with a relatively straightforward setup or something closer to those worst-case scenarios we talked about? Those MT and MT graphs, they highlight the outer limits of what's possible.
So they're like a reality check.
Exactly. A reality check that says, hey, don't get complacent. Don't underestimate the complexity here. And the funny thing is,
What's that?
even with these incredibly complex graphs, the researchers themselves acknowledge that they might not have even found the absolute worst case. There could be even more complex scenarios out there. Networks where achieving fault tolerance is even harder.
It's kind of like they pointed us to the top of Mount Everest and said, well, we're pretty sure there's an even taller mountain out there somewhere, but we haven't climbed it yet.
It's a good analogy. This research, it's not about giving us all the answers. It's about asking the right questions and pushing the boundaries of what we know. It's about challenging ourselves to find smarter, more efficient ways to build reliable systems.
So more research is needed.
Always. There's always more to learn. And in the meantime, for those who are really curious to see what these extreme cases actually look like visually, check out figures 1-3 in the paper. They show those MT and MT graphs we've been talking about. They're quite something.
A little visual reminder of just how complicated things can get.
Exactly.
Well, on that note, I think we've done a pretty good job of exploring the wild, sometimes unpredictable world of sensor networks. And if there's one big takeaway from this deep dive, it's that reliability is a journey, not a destination. And sometimes that journey requires a whole lot more sensors than we initially bargained for.
Well said. And with that, I think we'll wrap things up. Until next time, stay curious, my friends. And when it comes to sensors, remember, redundancy is your friend. All right, so today we're diving into the world of metric dimension. And I know it sounds a bit like something out of Star Trek.
Well, it's not quite warp drive, but it is pretty cool.
Yeah.
Yeah, it's all about figuring out the bare minimum we need, like sensors in a network to get a complete picture of what's going on.
Okay, so instead of starships, we're talking sensors. Give me an example.
Think of it like this. Imagine you're trying to pinpoint your location.
Right.
But you can only use the distance to a few landmarks.
Okay, so I'm 10 miles from the Empire State Building, 5 miles from Central Park, that kind of thing.
Exactly. Those distances, they give you a unique spot on the map. And in graph theory, we're doing something similar, just with, networks and data instead of maps and landmarks.
So we're talking about finding the fewest landmarks, the fewest sensors to get full coverage. Efficiency is key.
Exactly. And that's where metric dimension comes in. It helps us find that sweet spot between, how many sensors we need and how much information we can get.
But, and I'm sensing a but coming on, there's always a catch.
Of course. What happens when a sensor goes on the fritz or, takes an unplanned vacation?
Things break, yeah. And I'm guessing the solution isn't as simple as just adding a few backup sensors?
You'd think it would be, right? But that's where it gets interesting. This paper we're looking at today, it dives headfirst into this whole what if a sensor fails thing. They call it fault tolerance.
Fault tolerance. Catchy.
And what they found is that making a network like truly fault tolerant, well, it can get surprisingly expensive, like way more complicated than you might think.
How expensive are we talking? Like a few extra sensors or...
Think more along the lines of potentially needing twice as many sensors as you originally planned. And then, get this, potentially needing twice that just to handle a single failure.
Whoa, wait, hold on. Twice, then twice again. That...
Exponential growth.
Yeah.
And yeah, it can get pretty wild.
Okay, you definitely have my attention now. So how does that even happen? What makes these networks so sensitive in the first place?
So to really get into the nitty-gritty of this, the researchers, they actually built these special networks called EMP graphs. And they're designed to be like super efficient at their core, but then get really, really sensitive when even one little thing goes wrong.
EMP graphs? Okay, before we go full-on math wizards here, can you give me a visual? What makes these EMP graphs so special?
Imagine like a bicycle wheel,
Right.
right? You've got that central hub and all those spokes radiating out. Now picture each spoke is actually a chain of these little nodes, and only the one at the very end, that's the one that connects to other parts of the network.
Okay, I'm seeing it. So it's this chain link structure that makes them so fragile.
Exactly. You take out that one crucial sensor, the one at the end of the chain, boom, the whole thing's basically useless.
It's like cutting the wrong wire on those Christmas lights.
Perfect analogy. And the thing is, with these EMP graphs, to make up for that single point of failure, you might have to, like, double, even quadruple the number of sensors just to keep the same level of coverage you had before.
Wow. So you're telling me the way you arrange a network, how it's all connected, it can drastically impact how expensive it is to make it reliable.
100%. It's not just about throwing more sensors at the problem. It's about how they all work together, where they are in relation to each other. Like, think of building a bridge, right? One single support in the middle versus a bunch of supports spread out. It makes a huge difference if something goes wrong.
That's a great way to put it. And the paper, they didn't stop at just one failure, did they? What happens if more sensors go down?
You know, they had to take it up a notch. They called it chemotric dimension.
Chemotric dimension. All right, that sounds a little intimidating. What does that even mean?
So basically, they wanted to see what happens when, instead of just one sensor failing, what if two go down, or three, or even more? And what they found...
Well, I'm on the edge of my seat. What did they find when they went multi-sensor failure?
Well, it turns out that this whole exponential growth thing, it doesn't just disappear when you're dealing with more failures. It actually, it kind of sticks around.
So the more potential points of failure you add, the more the cost of reliability just, like, explodes.
Pretty much. Every additional failure you want to account for, it could mean another, like, massive jump in how many sensors you need. It's not ideal, to say the least.
Yeah, not ideal might be an understatement. It sounds like we need to rethink how we approach network design, especially for really important stuff.
Exactly. Like, imagine building something critical like a power grid, and you're suddenly realizing that a couple of sensor glitches could mean like a complete system overhaul.
It's a good thing we've got these researchers out there crunching the numbers and, sounding the alarm, right? This isn't just theoretical anymore.
Absolutely not. And the best part is, they're not just pointing out a problem. They're also, like, shining a light on what we still don't know.
Oh, so it's not all doom and gloom then. Tell me there's some good news in all of this.
There's always good news. It's just maybe not as straightforward as we'd like. See, while they proved this whole exponential thing can happen, they also admit that not every single network out there is going to be this extreme.
So there's hope. We just need to figure out when it's a manageable problem and when it's like abort mission.
Exactly. It's like they're saying, hey, we found this really cool thing, but now we need more research to figure out when it's a big deal and when it's not.
I like that. It's not just about finding the answer, it's about figuring out the right questions to ask.
100%. And they even left us with a little brain teaser or something to chew on. They want to know if it's possible to create a network that's, like, super efficient normally, but the cost of making it fault tolerant just skyrockets like crazy.
So find the network where the cost of reliability explodes the most. That's a challenge and a half.
Right. Like finding the ultimate breaking point. But that's how we learn, right? By pushing the limits and seeing what's possible.
Absolutely. This whole metric dimension, fault tolerance thing, these crazy MPREFs, it's definitely gotten me thinking differently about networks.
Me too. It's like this hidden world ticking away behind the scenes, and it's just as complex and important as anything we can actually see.
Well said. So next time you hear about like a big network upgrade or maybe a new sensor system going in, remember this conversation because there's a lot more going on than meets the eye. Who knew that something as seemingly simple as just placing a few sensors could be so complicated and so crucial to get right?
Ever get that feeling, that feeling like one little thing breaks and the whole system could go haywire?
Oh, absolutely.
Like imagine your security system, cameras everywhere, but then one sensor decides to take a nap at the worst possible moment.
Right.
That's what we're diving into today, this idea of fault tolerance.
Yeah.
How do you make sure things still work even when parts of them, well, don't?
And you might be surprised just how many places this pops up, honestly.
Oh, I bet.
Not just security systems, but think about sensors across a whole city. Or even making sure the data on your computer doesn't vanish if one part of the hard drive goes bad.
Essential stuff.
Yeah.
In our source material this time, they get into the nitty-gritty, starting with this concept of metric dimension.
Okay, yeah, sounds kind of scary, but it's actually pretty elegant when you break it down.
Break it down for us.
So, say you want to pinpoint an exact spot in a network. Any network.
Okay.
Metric dimension tells you the absolute fewest sensors you'd need so that by knowing how far away something is from each H sensor, you've got its location.
Ah, like a different kind of GPS, but instead of satellites, it's these sensors.
Exactly. And of course, the challenge is finding that balance, right?
Right.
Too few sensors, you can't locate anything reliably. Too many, well,
Gets pricey, I'm guessing.
you got it. And that's assuming everything's working perfectly, which, let's be real, isn't always the case.
Never is.
Exactly.
Sure.
So our paper, they take it a step further with fault-tolerant resolving sets. Basically, how do you design things so even if one sensor goes down, you're still good?
Okay, that makes sense. So just add a couple extra sensors here and there, problem solved.
Oh, if only it were that easy.
There's a catch, isn't there?
Always. The good news is, as long as you've got at least 2 points in your network, you can make it fault-tolerant.
Okay.
There's always some way to arrange those extra sensors.
So there's hope, but how much does this peace of mind cost us? We're talking double the sensors, triple. Give me the bad news.
Well, the upper limit on how many extra sensors you might need, it's not linear, it's exponential.
Exponential. That sounds significantly worse.
Yeah, it can be rough. The paper has the math for this upper bound, and let's just say there's some big exponents involved.
All right, I'm officially worried now. Tell me there's some good news here. Are there any cases where making a network fault-tolerant doesn't mean breaking the bank?
Don't worry, it's not all doom and gloom.
Okay, good.
There are some common networks where it's way more manageable. Think about a network that branches out like a tree. Pretty straightforward, right?
Yeah, easy to visualize.
Or imagine you've got people split into groups, and everyone in one group knows everyone in all the other groups, but nobody within their own.
It's like a giant networking event where everyone sticks to their cliques?
Precisely. That's actually a real-world example of what mathematicians call a complete multipartite graph.
Catchy.
Right. So in those cases, adding fault tolerance isn't so bad.
Okay, so no financial meltdown necessary.
Yeah, the research found that with those types of networks, you only need to add a number of extra sensors that's roughly equal to the original minimum.
So if you started with a reasonable number, you're still in good shape.
Exactly.
That's a relief.
Right.
But you mentioned earlier, this cost can be exponential, right? Are there actual cases where it gets that bad? Where making a network fault-tolerant, it's like bankrupt the city bad?
Yeah, unfortunately there are. And that's where this paper, it gets really interesting. They didn't just find the upper limit. They actually found networks where you do need exponentially more sensors just to handle one going down.
Okay, now I'm really curious. What do these worst-case scenarios look like? Give me the nightmare scenario.
So they call this the MTAR graph, and it's almost like it was designed to be as hard as possible for fault tolerance. Imagine you start with a network where every single point is connected to every other point.
Okay, so everything connected to everything. Got it.
Like a giant, massively tangled web.
Sounds like a mess already.
And to make it even more relevant, they label each point with a binary code, ones and zeros, like computers use.
So each point has a unique address, like a digital fingerprint. Okay, I think I see where this is going.
Now, here's where it gets really wild. They add this whole other layer to the network, a bunch of new points, and each of these new points is connected to specific points in the original set based on their binary code.
Hold on. So it's like this second layer is looking for specific patterns in the addresses of the first layer, and the more complex the pattern, the more connections you need.
Exactly. And what they proved is to make this kind of network fault tolerant, the number of extra sensors you need, it blows up exponentially compared to a regular network.
So this MCRAF, it's like the ultimate test. If you can make this work, you can make anything work.
Pretty much. It proves that these costs, they're not just theoretical, there are actual scenarios where you might need a crazy number of sensors just to make sure losing one doesn't break everything.
Which brings us back to why this research matters. Because who wants to go buy a million sensors if they don't have to, right?
Exactly. Or even worse, find out the hard way that your network wasn't as reliable as you thought.
Oof, yeah, not a good day.
So understanding the limits of fault tolerance, it's crucial. Whether you're building a city sensor grid or a piece of software, same problem at different scales.
Okay, my brain is definitely working overtime here, but this is fascinating stuff. But we've been talking about one sensor failing. What if you need even more redundancy? Like, what if the system has to survive multiple failures at once?
Excellent question. That's where caloric dimension comes in. It's like fault tolerance, but on steroids. Instead of one sensor, you're saying, can I still find everything, even if a couple of them go down at the same time?
So levels of paranoia, basically. K-metric dimension is like saying, I need this to work even if this many things go wrong. But I'm guessing it's not as simple as just adding K more sensors.
You're catching on quickly. The research actually shows, not surprisingly, you always need at least one more sensor for each extra failure you want to be ready for.
Okay, that makes intuitive sense, I guess.
But it gets trickier.
There's always a but, isn't there?
The researchers found that as you increase K, that number of failures you're protecting against, the cost of those extra sensors, it can grow exponentially again.
Wait, so it's not just that the problem gets steadily worse. Each step towards more reliability could need a huge jump in the number of sensors.
That's exactly what I'm saying. It's like climbing a mountain where each step gets exponentially higher.
Okay, that is daunting. But like you said before, it's not just theoretical, right? They found networks where this happens.
Well, just like with the one sensor failing, there's a type of network they found that proves this exponential increase really happens, it's called.
Don't leave me in suspense. What's this network called? What makes it even more complex than the last one?
All right, so it's called the MTK graph. And it's like they took that MT graph we talked about and put it through boot camp.
Okay.
Remember that second layer, the one connecting to the first layer based on the binary codes?
Yeah, like it was looking for specific patterns in those addresses.
Right. Well, now imagine instead of just one of those layers, you've got K copies of it, each with its OWN set of connections based on different patterns in those codes.
So it's like each layer is a team of detectives, and they're all looking for different clues in those codes to find the right spot.
That's actually a great analogy, and because you've got multiple layers all doing this at once, this MTK graph, it gets exponentially more complex than the original one. It's like they took the worst case scenario and hit it with a copy machine.
And I'm guessing just as bad for fault tolerance as they feared.
Oh, absolutely. What they confirmed is for this kind of network, the number of sensors to handle those multiple failures, it's not just double or triple. It explodes exponentially with each extra failure you're trying to be ready for.
So if climbing Mount Everest was hard enough, now you're doing it with a backpack that gets exponentially heavier with each step.
Now you're getting it. And that's why this research is so crucial, right? In the real world, you don't have infinite money, infinite resources.
Can't just throw sensors at every problem until it goes away. So what are the takeaways here? Why should someone who's not, deep into graph theory care about this?
Because whether we realize it or not, complex networks are everywhere nowadays. This research gives us the tools to make them tougher, more resilient.
From traffic lights in a city to, like, the software in my computer.
Exactly. It's not just about sensors. It's about understanding what it means for something to be reliable when the whole world's getting more and more interconnected.
We've gone deep today. Started with where to put a sensor, ended up questioning, like, the very fabric of a reliable system in a complex world.
Funny how that happens, isn't it?
It really is. And for everyone listening, I hope this deep dive has maybe inspired you to go explore some of this yourself.
Yeah.
Even in a world this complex, sometimes the toughest problems, they lead to the most elegant solutions.
Couldn't have said it better myself.
Until next time, happy diving, everyone. Ever get curious about, like the hidden costs of making sure all our tech doesn't just fall apart? Today, we're diving deep into the world of network fault tolerance.
Okay.
Specifically, how pricey is it to make a network, resilient to failure?
Right.
We're talking sensors, graphs, and a little thing called metric dimension.
Right. So it's like this. Imagine needing to pinpoint any location in a network, right?
Okay.
Just by knowing its distance from a few, strategically placed sensors.
Got it.
That's the idea behind this idea of metric dimension.
Okay, so finding the fewest possible sensors to get the job done.
Exactly.
But this paper you shared with me, fault tolerance of metric basis can be expensive.
Yeah.
Hints that it's not always so simple in practice, right?
Yeah. Yeah.
Especially when those sensors decide to, well, stop working. Yeah, that's right.
So hit me with it. What's the catch?
It's a bit counterintuitive, right? You'd think, okay, a sensor breaks down, let's just add a few extras and problem solved.
Right. Backup sensors, easy.
Yeah, exactly.
Yeah.
But this research kind of throws a wrench in that.
Really?
Yeah, it shows that while some networks behave nicely, like you can add sensors, increase that fault tolerance at a predictable rate, this paper demonstrates that that's not always the case.
Interesting.
In some networks, the number of sensors that you need for that fault tolerance, it explodes exponentially as the network grows.
Exponential. Okay, so not just like a little bit more expensive as the network gets bigger, but like way, way more.
Yeah, it gets out of hand quickly.
So what makes some networks so much more demanding in terms of this fault tolerance than others? Okay, so think of it like this. Imagine a network structured, we can think about it visually, like a bustling city center, right?
Okay.
With roads going every which way. So lots of connections, very dense. That's our densely connected hub.
Okay.
Now picture suburbs connected to this hub, but with limited entry and exit points, right?
Right.
So you've got this dense part and then these spokes coming.
I see it. Yeah.
This type of network, the researchers call this an EMPTech graph.
Mount graph, got it.
It throws a real curveball at this idea of fault tolerance.
Okay, I'm starting to see why. Right, because you've got these two distinct parts of the network, the hub and the spokes.
Exactly.
But why does that create such a headache in terms of keeping the network running smoothly if something breaks down?
Okay, so because of those limited connections between that hub and those spokes, right?
Right.
If a sensor in that densely connected hub goes down, it's not the end of the world.
Okay.
Other sensors can kind of pick up the slack because there's so many
Or
connections.
I think get a cover for each other.
Exactly. But if you lose a sensor on one of those crucial spokes, well,
It's like that sensor was the only one with a clear view of what's happening in that part of the network.
precisely.
Yeah.
To maintain accurate location data, even with, let's say, a single sensor failing, single point of failure in those spokes, you'd almost need a sensor for every single connection point from the hub to those spokes.
Because if one goes down, there's no redundancy, there's no backup.
That's right.
That's fascinating.
Yeah.
So the bigger the network grows, you add more spokes, more connections.
Right.
The more those potential single points of failure multiply. And so we're not just talking about adding a few extra sensors, but potentially a massive increase in the number of sensors you need just to maintain that same level of reliability.
Yeah, you're absolutely right.
That's where the expensive part of this whole thing comes in, I'm guessing.
Exactly. It's not a linear relationship. You can't just throw a few more sensors at the problem. This paper shows mathematically why that's the case.
So this EMP graph with its hub and spoke structure really throws a wrench into our, simplistic more sensors equals more robustness kind of idea.
Yeah.
But the paper doesn't just stop at one sensor failing, does it?
Yeah.
It cranks things up a notch.
Yeah, you're right. It introduces this concept of K metric dimension instead of just one sensor going haywire. What if we have like K number of sensors malfunction?
Okay, so now we're really talking about multiple points of failure happening at the same time.
Exactly.
Does that exponential growth problem come back to bite us again?
Unfortunately, yes. The researchers found that this issue persists even with these multiple sensor failures. And here's the thing. It's not just limited to those hub and spoke networks. It highlights like a fundamental challenge in how we design and think about these networks.
So as we build more complex networks, things like power grids or air traffic control systems or something like that,
Right.
this fault tolerance problem, I imagine, becomes a much bigger deal, right? Because even a small failure in one sensor could kind of cascade into something much larger.
Absolutely. Imagine a power grid, right? With this intricate web of connections, if we don't account for the possibility of multiple sensor failures, a small outage in one area could ripple through the entire system.
And the costs of those cascading failures, both in terms of, money and just like disruption to people's lives, could be astronomical.
It's a big deal.
So how do we even begin to grapple with this challenge? It feels like we're walking a tightrope here between, wanting a system that's really robust and reliable,
Right.
but also not breaking the bank in terms of how many sensors and how much redundancy we have to build in.
It's a delicate balance for sure, and this research serves as a wake-up call. We can't
Mm.
just assume that throwing more sensors at the problem will magically solve it. It demands a deeper understanding of the network structure and a more strategic approach to where we actually place these sensors.
It's like we've been so focused on just building networks that work
Right.
that we haven't spent enough time thinking about how to make them truly resilient when things inevitably go wrong.
Precisely. And that's where this paper gets really interesting. It doesn't just present a problem, it also kind of acknowledges that there's still a lot we don't know.
Oh, really?
Okay.
Give me the cliffhanger here.
Well, the authors themselves raise a really intriguing open question. Can we find a more precise way to calculate the difference between the regular metric dimension and the fault-tolerant metric dimension?
Okay.
Right now, it seems like we're working with this kind of worst-case scenario estimate, which, as we've discussed, could mean we're installing way more sensors than we actually need.
Right, because we're just assuming the worst possible thing will happen.
Exactly.
So it's about finding a tighter bound, like a more accurate way to assess the true cost of making a network resilient.
Yeah,
Because maybe it's not as daunting as it initially seems.
right. And that's just one of the open questions. The paper also hints at these real-world implications of all this research. The practical challenges of actually taking this theoretical knowledge and translating it into the actual design and implementation of networks in the real world.
It's fascinating how this paper reveals, this hidden complexity
Yeah.
in something that we just like expect to work, right? Like
Yeah.
a network that just keeps running even when, well, parts of it fail.
Yeah.
It's like we've been so focused on like building the car itself that we haven't really stopped to think about, well, how do we make sure the engine keeps running even if a few of the spark plugs are busted?
Yeah. That's a great analogy. And I think as we rely more and more on these complex networks for everything, communication, infrastructure.
Everything, yeah.
Yeah, critical infrastructure, all of that. Understanding these kind of hidden complexities becomes even more important, right?
Yeah. Makes you wonder if we should be asking like tougher questions about the systems we depend on every day.
Mhm.
Not just, hey, what can this network
No.
do? But what happens when something goes wrong?
Yeah,
And, what happens then?
exactly. And not just what happens, but, how much does it cost us to prevent those failures from happening in the first place, right?
Right, yeah.
This research really prompts us to think about, like, the trade-offs. How do we balance building a network that's, like, super resilient and robust
Right.
with something that is actually financially feasible to build, right?
Because a perfectly fault-tolerant network, sure, it sounds great, on paper, but
Yeah.
in the real world, like there's always a budget. So where does that leave us? Like feeling a little powerless.
No, not at all. I actually think this research is, it's pretty empowering when you think about it. It gives us, a new lens to view these systems through, like a deeper understanding of the challenges and what some of the solutions might look like, right?
Yeah.
It's about, like you said, asking the right questions, both as people designing these systems, but also as the users who rely on them.
So it's not, throwing our hands in the air and going, it's too complex.
Right.
It's more about going into this, with open eyes, with a little curiosity.
Exactly. And who knows, maybe by, talking about this more, by shining a light on this part of network design that people don't think about a lot.
Right, right.
Maybe we spark some really cool new ideas, new innovations.
New ways of doing things.
New ways of building these systems that are both really strong and resilient,
Right.
but also don't cost an arm and a leg.
Now, there's a thought-provoking note to end on. It's not just about the networks themselves, but it's that conversation about how we make them better. And maybe, just maybe, this deep dive will inspire someone out there to find, that next breakthrough. That's all the time we have for today's exploration of fault tolerance. But, this conversation, it doesn't have to end here. Until next time, keep those minds curious.